Everybody, can you see my screen?
Yes,
Yes,
Dr.
sir.
Ali.
Okay. So as you know that we are discussing the transient stability, and we have looked at breaking resistor method, extensively, and also we'll be continuing the discussion on the transient stability. So we'll be looking the much more details and some other methods for that stability. Uh, Here in this slide, you see I have mentioned several methods, I think at least 10 or 11 methods. Those are mostly used to maintain the transient stability of the large power network. So, for example, the first one we discussed, dynamic braking resistor or series dynamic resistor. And then there is fault current limiter. Maybe you remember before once I mentioned about this one. So today I will be discussing this on that fault current limiter. And then there is TCSC, thyristor control series capacitor, then static Ward compensator, then unified power flow controller, and static synchronous series compensator, SSS, then static synchronous compensator, STATCOM, static synchronous condenser or capacitor, which is that synchronous motor. And among energy storage, although there are various types of energy storage, but these two types have been reported for transient stability enhancement, especially when there is synchronous machine. So now you see the number one, the braking resistor and fault current limiter, number two, and number five, unified power flow controller, and last two. So this means these five, number one, number two, number fifth, UPFC, and then last two. Those five methods are mainly used to control the active power. And then the remaining methods, number 3, 4, 6, 7, 8, are used to control the reactive power. So therefore, just keep in mind that braking resistor, fault current limiter, UPFC, and then last two energy storage are for active power control. Although energy storage and the number fifth UPFC, they have the capability of both, but mainly they have been used for active power control. And then for reactive power control, TCSC, SBC, SSSC, STATCOM, and then synchronous condenser are used. So today we will concentrate on that fault current limiter. So this is very well known and then realistic method. This has a real application in real power grid. So now that fault current limiter, that is also again different types. So that I will be showing you and discussing. Everybody see the first here, superconducting fault current limiter. Like for example, among the energy storage, there is superconducting magnetic energy storage. Similarly, fault current limiter, but it is called superconducting fault current limiter. So therefore, this is basically a coil. This is a conductor, but it works in superconducting mode. So superconducting means, so at first you don't look this diagram. This is not the realistic diagram. This is for the simulation purpose. In any simulation software, this, the inductor and the in parallel resistance is used with the help of two switch. So this is the simulation model. That's why in the title I have written model of superconducting fault current limiter. Now in real practice, it's just a coil, only the L. There is no, or you cannot see any resistance. So let's have it take you to that whiteboard for a moment. Then it will help you to understand. So we are discussing that SFCL, superconducting fault current limiter. So it's basically, for example, we have that three-phase line going on, A phase, B phase, C phase. That SFCL, they are connected in series. Therefore, as I said, it's just a coil, superconducting coil. It's just a coil. Now, you see, of course, these lines have their own L and R, that you know. That is the line R and then line inductance. So each line have the L and R. Now this is, I mean, although this looks like the L, but basically its inductance value is very small. Here in the actual line, the inductance value is pretty much higher. But here, when I am putting another coil, this does not mean that it has very high value. It has very small value, these inductors. Now, that's why these are called the limiter. Instead of telling that inductor, these are called the limiter because they will work during the fault current. I mean, they are always connected in line. There is some sort of loss. You can say that I square X loss. There is reactive power loss, but very less as compared to this actual inductance, which are already placed online. Okay, and then so therefore fault current limiter means everybody assume this is a coil which has very small inductance. Now, why it is called superconducting? There is a refrigerator. With the help of the refrigerator, continuously it is being cooled, this coil. So therefore, R is 0. That is the definition of that superconducting fault current limiter. That it's a coil, it has very small inductance, but its resistance is 0 because there is a refrigerator. That refrigerator is maintaining the temperature. So why? Because if you don't do that, because these are the line, in all three lines, the current is flowing. For example, this is A phase current, this is B phase current, C phase current. If you don't put the refrigerator, then resistance will not be 0. You know the property of any conductor. Once current flows, then there will be, gradually it will heat up and it will develop some resistance. That's why, because it will continuously current is flowing, that's why to maintain resistance 0, there is a refrigerator. So because the resistance is 0, accordingly it is called that superconducting fault current limiter. Now the thing is that how it works. As I said, that it is placed along the line together with the line inductance resistance. So how it works? So here everybody say, just think about any of the line. It is the same for all three phases. For example, I am plotting this one, this FH current. This is the FH current. Now, just assume that whatever it is 1.0 per unit ampere current is flowing through this line, and this is the normal current. Now suddenly fault happened somewhere along the line. Something happened. This line means these are going on and they are connected to the rest of the network. Somewhere fault happened. Consequently, along this line, this IA current magnitude will increase. Now you see that IA current magnitude will increase, meaning that increased current has increased, that increased current is flowing through this SFCL. Even though there is a refrigerator, but that current is flowing. Therefore, depending on the current magnitude, it might happen that it is no more the superconductor. It fails. It cannot maintain the R0 even though there is a refrigerator. Because suddenly that current magnitude, not just current magnitude, maybe 2 times, 3 times, and 4 times higher. Depending on this increased current, the superconductivity fails. And then what happens? Actually, it appears as a resistance. It looks like that it's a high value of resistance. So instead of R, it becomes like R, really high value of R. And that R, because it is in series, that R will impede the current increasing. Next time it will be like that. So therefore, SFCL, superconducting fault current limiter, during normal condition, it's just a coil. For example, just a coil with very low inductance and R is 0 with the help of refrigerator. Once there is fault and then fault current magnitude is higher, then the superconductivity fails and its resistance increases. That is the property of that coil, that until a certain value it is fine. For example, up to now it is fine. Once it goes beyond that, then it cannot maintain superconductivity. That is the property. And that is the difference between this coil and this type of coil. They are like inductor, but this is different type of coil. That's why it is called fault current limiter. Its magnetic properties such that once current increases certain value, whatever technique you use, you try to cool it down, but it cannot. Its resistance increase, and it appears as a very high value of resistance, and that impedes the fault current. And then what happens, that for example, fault happen, that there is circuit breaker along the line, those circuit breaker gets open, right, to disconnect the fault, to remove the fault. You open the circuit breaker. I mean, that circuit breaker will automatically open within 5 seconds. Now see the line. One circuit breaker open, meaning that in this line current is getting zero. No current is flowing. But what happens, by then this coil already became unsuperconductive or non-superconductive because its resistance increases, it got heated up. So even though the circuit breaker opens, it breaks the current, no current is flowing, but immediately these coils cannot be the SFCL. Assume that your refrigerator is continuously working. Even though refrigerator is working, immediately it cannot be a superconductor. It, you cannot maintain R0. It takes some time. So that's why when it changes from superconducting mode to that fault current limiting mode, that situation is called the quench. I think you all know this word, quench. If you Google that quench, then you will get that term with regard to fault current limiter. So quench means that it is no more the superconductor. It has a high resistance. It has a high impedance. That is called the quench. So this means quench happens, and then also the circuit breaker open, but immediately it cannot transfer from quench mode to superconducting mode. It takes some time because already its superconductivity got damaged and it gained high value of resistance. So it takes some time. This is called the quench extinguish time. To get back to that superconducting mode, it needs some time. Now the question is, as I said, that quench occurs and then it takes some time to get back to that superconducting mode. Now by then, like circuit breaker open and close, and assume that still this coil is not fine, it did not return back to that SFCL mode, but then again another fault happened along the line. So therefore it may happen that once the fault happened, because it is not anymore that superconducting fault current limiter, it may not help. So that's why in real practice, instead of one coil, for example, I was showing you that this is that SFCL, there is one more coil in parallel with the help of a switch. This is the configuration. So therefore, this current was flowing, IA current, and you see, because of this property, increased current, then this changed, this became a high value of resistance, and then that, which is I'm calling the quench happened or quench occurred. Then circuit breaker opened, but it will take some time to go back to that SFCL mode. By then there can be another fault or another issue. Therefore, there is another parallel set. What will happen? This switch will be connected. So therefore, in case there is any fault, this will work as a superconductor. And then again, it will take time, circuit breaker will open, this will be under that quench mode. By then this will be fine. By then this will be fine. So in that way, like at a time, so that at least this one or this one operates, always there are two in parallel in real practice, these fault current limiters. Everybody, could you follow me?
Yes, sir.
Okay. Now you understood that basic principle of SFCL. Now, one thing is that as you can see, although I said that the SFCL has very small value of inductance, but there is, but there is. That's why always, even though during normal operation, there is some I square X loss, which is that reactive power loss. I mean, reactive power loss is happening through these coils, so there is no question with that. But I'm talking about this SFCL that during normal condition, because it has even the small value of inductance, but it forms I square XL. Because these are the AC line, of course these are the AC. So they have the frequency. So XL means 2 pi FL, whatever the small inductance, it will have some reactance. And that causes some reactive power loss. So therefore, that is one drawback. You can say that although it works very nice, I mean, this is proven technology. To limit the fault current, this is well-known and proven technology, widely accepted technology by the industry. But there are two drawbacks. One drawback is that even the normal condition, it provides some reactive power loss. In addition, to maintain superconductivity, you need a refrigerator. That incurs cost. So therefore, two drawback is that you need refrigerator in order to maintain superconductivity to keep the R0, and then there is some I square XL loss. You can argue that this loss is smaller than that loss. Of course, that is true, but still there is some loss. That's why now the power engineers have explored other type of fault current limiter. This is at the early stage, like at least 100 years ago, that SFCL was established, developed this concept. But as I said, there are two drawbacks. One is this I square X loss, and then the superconductivity maintaining. That's why there are other types. Let take you there. Okay. So there are other types like called DC resistive SFCL. You see the structure is different and there is diode. So we are coming that later. Now, this was my first slide. I was telling you that this was not the realistic picture. This is the simulation model. Like if you see, for example, Simulink or PS-CAD or ATP, any power simulator, then you will notice that SFCL is modeled in that way for the simulation purpose. Because you are simulating, it is not realistic. This is not the real coil. So you cannot change it after the fault. So what is done for the simulation model, you notice everybody, there are two switch 1 and switch 2. And this represents that SFCL coil, and R represents that quench mode. This means some fault happened and then L will be changed into the R. So therefore, how to do that? So during normal condition, this switch is closed and this switch is open. Everybody see the sequence, this switch is open, meaning that, and this is the picture for on phase, like phase A or phase B or phase C. So switch is open, so current is flowing through this way because this switch is closed. So this is representing that SFCL. Now once fault happened in your network, you are simulating fault, then because you have to represent this on in terms of high value upper, this is put high value upper, then this switch is open so that no current is flowing. So this switch is closed and current flows that way. And then it limits the current. Therefore, everybody keep in mind, that's why I have written model. This means this is the simulation model. And then I have written all those information you see. Switch SW1 is closed and SWT is open. That is the like normal mode. Inductor rail is in the circuit and its value is kept very low. I already told you. Once a high current is detected, the switch W1 is opened and SWT is closed. And R is a high value of resistance is brought in the circuit to limit the fault current. So this is the basic feature. Now, as I told you that there are two losses, you have to maintain superconductivity and there are some reactive loss, even though the value is very low for this inductor. Now, to overcome that limitation, in recent days, there are several improved versions. So everybody see, one of the version is a DC resistive SFCL. This means it is superconducting fault current limiter. Still there is refrigerator, but in this case, in this structure, you can reduce, you can eliminate that I square X loss, reactive power loss. So what is the technology? Technology is that when, again, this is the picture for one of the phases. For example, for phase A, then you need similar structure for phase B and for phase C. Now, what is happening? This is your line, for example, phase A. And as you can see, there is the diode. This is the diode bridge in electronics. If you remember, what is the function of the diode bridge? It can convert into DC. Because, I was telling you with that whiteboard that here the AC is flowing. But during normal condition, continuously there is AC loss, which is I square X loss. So to avoid that loss, what is happening? You see, the AC current is coming, it is diode, so it became unidirectional. And then the C, it is the anti-diode, so current cannot go. Current will flow through this path. So this is that coil, LSC, superconducting coil, which is SFCL. Now that resistance, again, as I said, this is the DC resistor SFCL model. This resistance is not realistic. Really, when there will be high fall current, then automatically this inductor will convert it into resistance. Here the simulation model, so it is in series and it is showing, you see, that variable sign. So therefore everybody see, for example, the normal condition, current is flowing, it is going through this diode D1, it converted into DC because diode will do the unidirectional, and that unidirectional current is flowing here. At the beginning, of course, RSC is 0 initially during normal condition. And then because this is DC, what will happen for the DC? It will be short circuited. So there is no loss here. So just current is flowing and then it will go in that direction. That is for the positive half cycle. This is the way. For the negative half cycle, this is the way again. So in that way, for both positive and negative half cycle, it works. Now, that is the normal condition. Once fault happen, because these lines are connected to the rest of the grid, somewhere fault happen. So the fault current magnitude will increase. So this means that line current has increased. And of course, keep in mind, this is the AC current. That increased AC current is flowing through the diode. Of course, you can assume that these diodes have that withstanding capability up to that level. So it is going and that it converted into DC. Therefore, here also corresponding high value of DC current will flow, and depending on the magnitude of that high value of DC current, it will quench. It will be quenched, meaning that it will be no more the superconductor. It will appear as a high resistance, which is shown here. And then the fall current will decrease. And then it is going in that way. Similarly for the negative half cycle. So therefore, it is called DC resistive SFCL. The previous one simply SFCL, meaning that you can assume that this is connected with the AC system. Whether it is single page or 3-page, it is the AC system. Once it is the DC resistive, of course, this is connected to AC system, but inside mechanism, that main coil is connected in the DC circuit, in the DC path. So what is the benefit? The benefit is that during normal condition, there is no I square X loss because you already converted into DC. This portion is DC. So there is no frequency. So therefore, it will be just short circuit. There is no I square XL loss. So you can avoid some loss. So that's why many industry has adopted this technology. But still you need a refrigerator. According to this concept, still you need refrigerator. But you are avoiding that, you are eliminating that I square X loss. So accordingly, it is called DC resistive SFCL. So, everybody, could you follow me so far?
Dr. Ali, I have a question, please.
Okay.
So during normal condition, would this be energy storage or no?
It will store some energy. So it's a good question. So therefore it will store some energy. That's why in real practice, there will be actually switch here and then the diode here. I am showing another picture.
Okay.
Can you see this one?
Yes, I see.
Yeah. So probably you wanted to. So what was your full question?
I said during normal condition, would the inductor would be like energy storage, and we can store it locally.
Yeah. Exactly. It will store some energy. That's right. Because this is DC. So that's the only question, right? Yeah.
Yes.
Yeah. So I will showing you something. So I will when I will be going there, then I will elaborate.
Okay.
It will store the energy. That is fine, but sometimes there is some drawbacks. So that's why you need another diode. So I'm coming that point later.
Okay.
Okay. So at this point, at least everybody understood the difference between that DC resistive SF cell versus this one. So here, like both you need, you have to maintain superconductivity, you need refrigerator, and there is AC loss. So here the difference is that there is no AC loss here, but of course there is refrigerator cost. Now we want to avoid that superconductivity. After that, after developing this on, power engineers have confirmed that no, let's omit that superconductivity as well, because that is taking much more. This is very costly thing because it needs the superconductivity. You need a refrigerator. So that's why there is bridge type Hall current limiter. Again, as you can see, that this configuration is very similar to that the previous structure. Of course, there is some diode and switch, but at least this arrangement is the same. And then what you can see the new thing, you see there is a shunt or the parallel path. And the LSH, SH stand for the shunt path or the parallel path. LSH and together with a small resistance. Sorry, together with a resistance. So LSH and RSH. Now, what it does, how it can avoid that superconductivity. So in this case, this is the main coil. This is not the main coil. Can you see in the DC path, there is on inductor and there is on resistance. But in this case, this is not that main coil that will limit the fall current. Main coil is this one. So what is the technology? This inductance and this resistance is high, and that is placed in parallel. And this inductance and this resistance is almost negligible, like 0.0001, like that, very small resistance. So during normal condition, what happens? As you can see that AC current is coming from here, for example, for phasor. And then there can be very little leakage current, but almost there is no current flow through this path because this is very, very high as compared to this path. So you know the property of that resistance and then conductor. If they are equal, then equally divided. And when there will be close to short circuit path, then most of the current will flow through the short circuit path. Therefore, there can be small leakage current, but in real practice, it does not go. So therefore, during normal condition, you see, current comes here, AC, and then converted into DC, and that DC goes through this path. Here the switch is closed. During normal condition, this switch is closed. Now that switch can be electronics based, power electronic based, IGBT based, or GTO based. So at this point, momentarily assume that it's a switch, and during normal condition, the switch is closed. So that's why AC current is coming, it converted into DC, and then it is flowing in that way. So this means you see that because this is DC, so there is a small inductor and that becomes short circuited, and there is resistance. This is very, very small, as I said, like 10 to the power minus 5 or 10 to the power minus 3 ohm, very, very negligible. So you can argue that there is a small loss, that is fine, but the most of the current is flowing through this path. So because as I said, in this path, the resistance is very, very small as compared to this path. So, but again, some industry says that they have noticed some leakage current was flowing, but some other companies, they have never noticed any leakage current was going during normal condition. The problem is that if during normal condition much current flow through this path, then there will be loss. We want to avoid those loss. So that's why we want to avoid the reactive power loss, as well as we want to omit the superconductivity refrigerator. That's why we want to adopt this technology, this structure. So you see that during normal condition, once again current is flowing through this way, there is very little resistive loss, but that is fine. And then this switch is closed. What happens? Fault happened. Fault happened means this current will be higher. So therefore you see what will happen? Higher current is going, converted into DC, but then there will be a controller. In this structure, there will be a sophisticated controller, because initially this switch is closed. Depending on the magnitude of current in this path, this switch will be open. Because the switch get opened, so no more current is flowing through this way, it got disconnected, current will start flowing through that path. And that is the reason here the inductance and then resistance are put higher, so that they can limit the current. So therefore the benefit is that because you are not putting this coil, actual fault current limiter, this coil here, so you don't need to maintain the superconductivity. And that is the reason you don't want to allow even a small leakage current through this way, so that it does not change its resistance. So there is no superconductivity issue here, because you are not allowing current flow here. Now everybody see the Uthman asked on question, because here that the DC, so as I said, for DC the inductor will be short circuited, but it will store some energy, that half Li square, right? So it will store some energy. There will be of course I square R loss, even though it's small, but it will store energy. And as I said, that during fault this switch will be opened. This switch got opened, but this inductor already has gained some energy. Now there can be some spark or other issue of these diodes. That's why you see there is one diode. What will happen? Everybody, current was coming from top and it was going, switch got open. So current will start flowing through this way, through this diode, and it will be in that way. So this is called the freewheeling diode, DF. Here you see there is subscript F. Yeah, can you see DF? It is called freewheeling diode. This means when this line got disconnected, you have to consume that inductive energy, the energy stored, so that there is no sparking or other problem. So that's why current flows, and after a while, because no more current is coming, only this is the consumed energy, stored energy. After a while, it will decay, it will go away. So therefore, the main thing is this one. This is that fault current limiter, this path. And this is very popular. If you Google bridge type fault current limiter, you will get lots of articles and lots of research. And this is the very, very, high quality technology. In recent years, BFCL, it has a lot of application in wind energy system, conventional synchronous machine, and other type of, even with the photovoltaic system. So everybody, could you follow me?
Yes, Daddy.
Yes, sir.
Okay. So then there is one more fault current limiter. Now, how to, regarding that switch, as I said that during normal condition, switch is closed, and during fault you have to open so that this path on. So now there are lots of parts, lots of control technology have been developed just to control the switching for this switch, open and close. So for example, here one of the example, closed loop control system for BFCL. So as you can see, for example, this is the grid, and this is the bridge type fault current limiter, and then there is transformer, and then synchronous generator and other generator. Now you are designing that, you want to design a controller for that switch. That is the goal of this picture. So you see what you are doing. You want to send a signal here, IGBT gate signal, control input 0 or 1. So meaning that when it is 0, meaning that is the closed. When it is 1 means that is the open. So you are taking the control input. Again, for example, before we discussed, in case of braking resistor, total kinetic energy deviation. So meaning that you have a group of generators from where you are taking the input and then you are passing it through some nonlinear controller, in this case fuzzy logic controller, and then it is some saturation, it is producing that RSH means this value. It's one type of control technique. There can be other type of control technique. This is just one example. And then there is a comparator circuit here. Comparator means it is comparing with that 7 ohm value of resistance. This is one specific example. As I said, control structure can be different type. So it says that if RSH value less than equal to 7 ohm, then IGBT gate signal is 1. Otherwise, IGBT gate signal is 0. This is the logic or algorithm. Then IGBT gate signal goes and accordingly it gets on and off. So therefore, there can be various types of controller for this switch to get it open or the closed. This is one example. This picture is showing that from the system it is taking TKD and accordingly it is producing that IGBT gate signal. Now here the example is IGBT, insulated gate bipolar transistor, but even it could be GTO, gate turn-off thyristor. So therefore, for your understanding at this point, you assume that this is a power electronics based switch. During normal condition, switch is on, and during fault condition, with the help of the controller, it will get open so that the fault current goes through that shunt path. Okay, now then moving forward, there is other type. Can you see the name? Parallel resonance type fault current limiter. It is called parallel resonance type. So as you can see, everybody's structure, it is similar to that BF cell, bridge type fault current limiter, just we discussed, but there is on capacitor. You see the difference here? In this case, it was resistance inductance in series, and they limited the fault current. In this structure, you see, inductance is in this path, but then in parallel, there is a capacitor, and together with the capacitor, there is a resistance value. This resistance is not that big. So that is the difference between this, and in this case, both are larger. Both inductance and then resistance is larger. But in this case, there is high value of inductance, there is high value of capacitance, but this resistance is small. Even you might eliminate. If you Google and if you see that parallel resonance type fault current limiter, some reports says that no, you only need the combination of L and C. But some power industry say no, you may add a small resistance that will improve the performance. Now, how it works, because it is the parallel combination of L and C here, I mean, working principle is the same. During normal condition, DC current will flow. You see, there is a switch is closed. Once fault happen, switch will open, current will flow through this path. But because it is in parallel L and C, that's why it will form a parallel resonance. So you know the series resonance and parallel resonance. In case of the series resonance, when XL equal to XC, in a series circuit, inductive reactance become capacitive reactance, and then the XL and XC cancel. In the circuit, impedance become very low, and the current become very high. On the other hand, the concept of parallel resonance, during fault condition, current will flow here, but they will offer very high value of impedance. That is the property of the parallel resonance. So series resistance offer small impedance. Parallel resonance offer high impedance. And that high impedance will impede the flow of the current, reduce the magnitude of current. That's why it is called parallel resonance type of fault current limiter. I think I have written it here, that large impedance introduces when resonant frequency becomes equal to power system frequency. At that frequency, they will exhibit high value of impedance, large impedance. And that just if you, I believe from circuit standpoint, you know what is parallel resonance, what is serial resonance, exactly the concept of parallel resonance. They will offer the high impedance, and then they will limit the fault current. So therefore, the difference between this one, I mean PRFCL and then that BFCL, that in some cases it has been found that this structure work better than that one. I mean, not always, in some cases. So there are some reports available, especially in case of wind generator system, that this system provides better performance or better response as compared to that BFCL, or even as compared to that DC resistive FCL, and of course as compared to that conventional SFCL. And then again for that parallel resonance type fault current limiter, because there is the switch, and during fault you have to get it open so that the current flows through this path. Again, you can design this switch controller. Again, it can be IGBT based, GTO based, or any other technique, and you can use sophisticated controller. For example, here there is one example. Again, that parallel resonance, similar type of diagram I'm showing, transformer and then synchronous machine, and for example, G1 to G10, 10 generators, and from all generators, you are taking the control input, and here there is controller, in this case, one term K1 constant multiplied by square of TKD. It may be fuzzy controller or other nonlinear controller, or even it can be PID controller. And then it produces that LSS value. And then again, there is comparator circuit. It is comparing with some threshold. And then accordingly, IGBT gate signal is getting 0 or 1 signal. Consequently, your that parallel resonance that is getting affected in the system. So therefore, unless you do research in this field, like I would not tell you, okay, concentrate on the controller, because if you Google PRN, you will get lots of hundreds of articles, and this control structure, different authors have used differently. So therefore, unless your research is in this direction, you don't need to go. You assume that including this controller, there is PI controller, PID, sliding mode controller, variable structure. There are lots of sophisticated controllers just to create that gate signal to get it on and off. Now, if you see the literature, you will see there is some performance comparison between that BFCL and parallel resonance fault current limiter. So for example, you remember, I think last class I was showing you this diagram, IEEE 30 bus power system with auxiliary devices. And it is 30 bus, and there are 6 generators, and there are 2 coherent group. This is one group and this is other group. And you notice here at the terminal of G1, generator on auxiliary device, here at the terminal of 6, auxiliary device. These auxiliary device assume that those are the fault current limiter, whatever the type is, either BFCL or parallel resonance type. So for this system, so simulation have been conducted putting on BFCL or parallel resonance BFCL here, and on BFCL or parallel resonance BFCL here for this system. And then the analysis have been made, and here you can see I'm showing you total kinetic energy response for 3-phase to ground temporary fault at position A for the system, and we are plotting total kinetic energy versus time up to 10 seconds, and you can see this curve, the fault happened, consequently there is high jump of kinetic energy. This is the steady state value, and then there is oscillation and it is going on. So without any controller, meaning that for this case, there is no BFCL or parallel resonance or any technology. But then see the red curve, it is using the BFCL. See the performance of fault current limiter. Here it was the magnitude of kinetic energy. You can see 10 to the power 11, very high, and then it is reducing the magnitude. And then this one with parallel resonance time. Here you can see much improved performance. That I said that not always, but at least if you read like 10 articles, in 5 articles, you will see the superiority of PRBFCL over the BFCL. You can see. So this is one of the example. So same thing it is happening. This is for the 1 LG temporary fault, single line to ground fault. And again, you are noticing when there is no controller, means there is no fault current limiter, the kinetic energy response is going high. And then BFCL is reducing and PRBFCL is reducing further. You see, quickly it is settling down. The BFCL, it is going somewhat upward and coming down, and here it is settled down. But parallel resonance, like from here, it is started settle down quickly. Same thing is happening here. So these are the sample response. Then of course, here the total kinetic energy response is plotted. But if you plot the fault current magnitude, and if you see the controller performance, you will see the similar performance. I'm just showing some example of total kinetic energy response. Everybody, could you follow me so far?
Yes, Dr. Ali.
Yes, Dr. Ali.
Yes, sir.
Yeah, these are pretty interesting. Like if you like to do like 2 theses or 2 dissertation, you can start working on these fault current limiter. You see, I mean, very popular and very well known. In the past, in my lab, 2, 3 students work. Dr. Sadi, Dr. Gilmanur Rasid, and Dr. Kamal. Dr. Kamal, who is currently working at FedEx, and Dr. Gilmanur Rasid, who is working in ABB industry in Senatobia, I mean near Memphis. And Dr. Sadi, he has been the faculty at University of Central Missouri. They all worked in this technology. So, I mean, they all graduated in 2016. So once those guys left, I stopped this research. But now after 4 years, I am sharing you this information. So of course, if you are much more interested, then you can do these things as well. Okay, so with that, now again, some questions that you have to answer. First, 2 numerical problems, and after that, there are some short quiz that you all have to answer about all fault current limiter technology. Okay, so first, everybody go these numerical problems. Please take your pen and paper and answer these. Everybody, please take your pen, paper, and calculator. A bridge type fault current limiter with a limiting resistance of 12 ohm per phase is used to maintain the transient stability of a 3-phase 13.2 kV 60 Hz 50 MVA 2-pole Y-connected cylindrical rotor synchronous generator. Assume a negligible limiting reactance. If the fault current magnitude is 1.2 times the rated current of the generator, then calculate the total power consumed by the limiting resistance. Moreover, if the power factor of the generator is 0.85, then calculate the shaft torque. So although the problem looks very long, but the calculation will not be too long. So everybody see what it says, that the bridge type fault current limiter has been used with a limiting resistance of 12 ohm per phase. So therefore, let me go back to that BFCL picture. This is the BFCL picture. So the problem is talking about this thing, this RSH. As I said, that there is R here, but this is the DC resistance, very, very negligible. So the main resistance is this one. This resistance, what I would recommend you, either you take a picture or you quickly draw this picture, diagram that will help you to solve that problem. Can you please quickly draw this one? Just the picture, you don't need to, explain this description, just the picture, so that many times we don't need to go back and forth here. So have you drawn this one?
Yes, doctor, I'm done.
Oh, okay. So everybody?
Yes, Dr. Ali.
Yeah.
Yes, sir, I'm done.
Okay, very good. Now see this picture in your note, and then see that bridge type fault current limiter with a limiting resistance. That limiting resistance of 12 ohm per phase, limiting resistance, that shunt path RSH. To maintain the transient stability, 3-phase, this. These are the synchronous generator specification. Now what it says, assume a negligible limiting reactance. This means that reactance value on top, that is negligible. So this means because no value is given, so you don't need to assume any value. And then it says, if the fault current magnitude is 1.2 times the rated current of the generator. This means when fault happens, everybody see, during normal condition, current is flowing. Now, and then, for example, at some point, the rated current is flowing. So once fault happened, that fault current magnitude becomes 1.2 times of that rated current. I'm sorry. So therefore, that is the question. Then calculate the total power consumed by the limiting resistance. Under that situation, what should be the total power consumption? That is the question. And also, if the power factor is 0.85, then calculate the shaft torque. So therefore, do you understand this part? So you have to calculate what is the magnitude of fault current. Because you see the very first line, that limiting resistance, that resistance 12 ohm per phase, that will actually limit the magnitude of fault current. And this statement says, if the fault current magnitude is 1.2 times the rated current. So this means what you have to do, from the generator information, in the third line, from the generator information, you have to find out what is the rated current. And once you get the rated current, then fault current magnitude will be 1.2 times of that current. That is the meaning. And that fault current will flow through that limiting resistance. You see your picture, that fault current will flow through that limiting resistance. This means there will be power consumption there. So that is the question. Calculate the total power consumption. Now, when it says the total power consumption, means total 3-phase power consumption. So of course, this 12 ohm, it is for per phase. So if you can calculate the power consumption for one phase, then you just need to multiply by 3. That will give you a total power consumption. Everybody, could you follow me?
Yes, Dr. Ali.
Yes. Can you please now calculate, everybody? So therefore, I mean, simply speaking, you just take this example that your fault current So your fault current is fully flowing through the upper path because already this switch has been open. So you don't think about that bridge part. Your fault current is flowing through that one. And that has 12 ohm value. And L is negligible, it says. So therefore, you find out how much current is going there. So therefore, I square R, that will be your per phase power consumption. And then multiply by 3. That will be the answer. That will be the first answer. And then there is the second part. Moreover, if the power factor of the generator is 0.85, then calculate the shaft torque. That is the second question. Everybody first calculate that total power consumption and let me know the result. Think, let me write down it here. Let me use a different color. Okay. So total power consumption, like I got 247.93 megawatt, and the shaft torque, this is 0.3 mega Newton meter. So this, you see, I have written in green colored. This is the result that you should be getting. Total power consumption 247.93 megawatt. Has anybody got so far?
Yes, Dr. I got the power value same.
Okay. And the next question is, if the power factor is 0.85, then calculate the shaft torque.
Yeah, I'm working on that.
Okay. Kamana, did you get the torque value same?
No, Dr. Ali, I'm still working.
Okay. So Manoj, did you get the power consumption value same?
Yes, Dr. Ali, I got it.
Okay. Lakshmi?
Yes, Dr. Ali, I got the same value for power consumption and I'm working on shaft torque.
Okay, great. Yeah. Amani?
No, Dr. Ali, I got something different.
Oh, far different?
Yes, sir.
Oh, maybe again your calculator is not helping you.
No, I think this time it's not my calculator. I think my numbers.
Oh, okay.
So first we find the rated current. I got the value. It's 2.187 K.
Kilo
Right.
ampere. Yeah, that's right. That's right.
Okay. Then we have to multiply that with 3 because we have 3 phase, right?
No, so you have to do one. You see, that current is the line current. See the
Yes.
problem. That is the see the last of the third line. It is Y connected. So for the Y connected, line current and phase current is the same, right?
Yes.
So therefore, the fault current magnitude will be 1.2 times of that you said, 2.186 kiloampere. Then you have to multiply by 1.2.
Mm-hmm.
That value will be the fault current for only one phase.
Okay, I got now.
Yeah. So therefore, then first you calculate using that current I square R. Then at last you multiply by 3 to get the total. Sindhuja and Venkat, are you doing?
Yeah, yes. I got the
Yes, sir.
total power consumption.
The same value?
Yes, sir.
Okay. The Sindhuja?
I'm working on it, Dr. Ali.
Yeah. So first calculate the rated line current and then find out the fault current by multiplying that number that you will be getting rated line by 1.2 and then use I square R and finally multiply by 3. Then you will be getting that result.
Dr. Ali,
Yes.
for the second part, do we need to calculate P value by using power factor?
Oh, of course. What is the
Shaft for the shaft
shaft torque?
torque?
Yeah, shaft torque is power over omega, right?
Yes.
So of course you need that active power.
Yeah, before I use the power. Yeah. Okay, I
Only
got it.
use the MVA, right? Yeah. Now
Yeah.
you have to convert into active power. That in the third line, that number 50 MVA, that is the rating, that is the apparent power. That is not the P, that is not the real power. So you have to multiply by the power factor. So 50 MVA multiplied by 0.85 divide by the omega. That omega you have to calculate from the information.
I got it, Dr. Ali.
Now you got?
Yeah, I got 274.95.
Oh, great. Now you do the second part. If the power factor is 0 point, then calculate the shaft torque.
I got the shaft torque.
The same result?
Yes, Dr. Ali.
Yes. Like I expressed mega Newton meter, you can express kilo Newton meter or other thing, but this is mega Newton meter.
Yeah, I also got the same value, Dr. Ali.
So you got the same? Okay.
Yes.
Okay. Sindhuja, did you get the first result? Venkat?
Yeah, yes, sir. I got the first one. I'm
The-
working on the second one.
Okay.
Chapter.
Lakshmi, did you get the right second one?
Yes, Dr. Ali, I got it.
Okay, okay. You might express in Newton meter or kilonewton meter. No problem. I just expressed in meganewton meter. That's 0.113 approximately.
Okay, Dr. Ali.
Yeah, but anybody you can express kilonewton meter or very long value Newton meter, no problem. So Amani, are you doing like torque
Yes,
equal
can
to
you see what-
power
Mm.
over omega in radian per second? So
Yeah, I got
for-
a 376.8.
yeah, radian per second. That's right.
Yeah.
And then power will be that 50 MVA multiplied by the power factor.
I got 58.82 for that.
Okay. So then after dividing by, like I expressed the result, you see green colored, I have written 0.1 mega Newton meter. So first you see Newton meter and then you can convert into mega. So you can check that it is matching.
Dr. Ali, I got 0.156.
Mega Newton meter,
Yes, sir.
156.
It's 156, not 113.
Oh. So how about the others? Did everybody get the same thing I didn't got, or what Aman is telling you got that number?
Can you repeat, Amani?
Sure, I got 0.156 for the torque. My power value is 58.82 mega. And my speed is 376.8 radian per second.
That is right. Yeah.
I think the power value should be 42.50 megawatt.
Manu, what is your power factor you use? 0.85.
I got 58.82.
No.
Oh. It's supposed to be 50 over.
0.85 multiplied by 50. So it should not be 58. You are multiplying 0.85. So it must be lower than 50. So Kamana, you said 42 point something, right?
Yes, Dr.
Yeah.
I just divided 50 divided by 0.85.
No, why you divided?
Because power factor is equal S over P. So maybe this is my mistake.
So this is the S, 50 is the S.
Yes.
So no, you are telling the opposite thing. Power factor is P over S.
Yeah, okay. I'm sorry.
Oh, right. You inverted.
I
Yeah,
check my list. I use my brain. So it's
you
P over S.
inverted. That's why. Yeah. Okay.
I'm sorry.
No, that's fine. Yeah. Sindhuja, did you get the first one? Or are we still calculating?
She's out of the chat, sir.
Oh, really? Oh, okay. I see. And Venkat, did you get the second one?
Yeah, I got the nearest value, but not the same.
Okay, so you see that sap torque is power divided by omega, radian per
Yeah.
second. So power is that 50 MVA multiplied by 0.85. And
Okay.
omega, first you calculate the synchronous speed. You see the 120 F over P,
F by P. Yeah.
and then convert into radian per second. So if you divide power by that radian per second, so you should be getting very close by this one that I have shown, 0.113 mega Newton meter.
Yes, sir. I'll try it.
Okay.
I got it, Dr. Ali.
Oh, you got now? Yeah.
Yeah, I got 0.1127. It's almost
Yeah,
1.
yeah, yeah. That is fine. Yeah, okay. Okay, then fine. Okay, okay. And now everybody read number 2. Read number 2. So for number 2, so will be this will be the answer. Sorry. So everybody read number 2. A 10 MVA, 5000 ampere, 3-phase Y connected synchronous generator with a 0.9 power factor employed SFCL to maintain the transient stability. And during fault, the SFCL consumes the power which is equal to the machine's rating. Then calculate the per phase resistance value of the SFCL, assuming the rated current flows through the line during the fault. Because you know this is SFCL, so directly it is connected in line. SFCL is the traditional one, very first one that we discussed today. So it has some resistance, and that resistance will consume power, and consequently it will improve the stability. Now it says that SFCL consumes the power which is equal to the machine's rating. Then calculate the per phase resistance. So the first question is, what is the machine's rating? What is the power value of the machine?
Yes, Dr. Ali, I got it.
Oh, okay. So you see the
0.12.
power 0.12 you got, Manoj, right? Yeah.
Yes, Dr. Ali.
Okay, great. So everybody see the power value is 10 MVA multiplied by the power factor, right? Yeah. 10 MVA multiplied by 0.9. So this means 9 megawatt is your total power. And then SFCL consumes that 9 megawatt. Then calculate the per phase resistance. So therefore that 9 megawatt is the total for 3 phases. So you divide by 3. So 3 megawatt will be the consumption for each phase. And then find out that resistance, assuming that the rated current flows. What is the rated current? At 5000 ampere. But that is the same for phase and line because this is Y connected generator. So therefore 5 ampere goes for both line or the phase, same thing. So based on that, calculate the resistance value.
That's the same value, Dr. Ali.
You got Lakshmi?
It's Amani.
Yes, Dr. Ali, I got 0.12.
Oh, okay.
Oh.
Aman, you said right? 0.12. Okay.
Yes, it's Dr. Ali. I got it right.
Amana, did you get?
Yeah, I too got the same one.
Yes, Dr. Ali, 0.12.
Okay, very good. Yeah. Okay, so therefore I am now scrolling. So let me save because I wrote down those answers. Now from second slide, now you answer those things. These are the, based on today's class, there are some conceptual questions that you have to answer. There are 8 questions, it's like 1, 2, 3, 4, and there is 5, 6, and there is 7, and there is 8. There are total 8 questions. So you please all answers this one. Read the questions and answer. So therefore, what we have to do, because this class time is not enough, we have only about 10 minutes. So as much as you can answer here, and then the remaining you can answer after the class. And then again, I have set up a Dropbox class quiz 2, where you have to upload. And I think I have set up the time until 9 p.m. So everybody, you work now until the end of the class, and then you keep going, and then I'm allowing you another 2 hours until 9. By then, you please upload these answers on the Dropbox name class quiz 2. So therefore, already these questions are given, at the as part of this will be class 810. So you can see on the eCourseware that this class lecture is posted. So in the last 2-3 slides, you can see this question. So you look and then you just write down the answer and upload your answer on Dropbox class quiz 2 by 9 p.m. Now everybody will try as much as you can answer here. You can. It would not be too long. Answer.
Dr. Ali,
Yes.
can you please give us time until tomorrow?
Okay. Until tomorrow.
Yes, please.
Until tomorrow. Until tomorrow. Until what time?
Before noon. Maybe by noon. I will do it by noon.
By tomorrow noon.
Yes, sir.
Okay. Okay. So therefore, I will after the class I will update the submitting time.
Thank
So
you very much.
Until tomorrow noon, you said?
Yes, sir.
Okay. So therefore, everybody then I will update that Dropbox until noon. Until noon tomorrow.
Thank you, Dr. Ali. Thank you very much.
Yeah. So everybody think very carefully and then see. And then because you see the questions are related to BFCL, SFCL, DC resistive, all like already there are previous slides we discussed, and I'll be uploading that video, my video lecture. So therefore all are the sources and you can answer based on that. And you are free to use any resources, class material, you might Google, whatever you can do. But you have to answer these. There are 8 questions.
Dr. Ali,
Yes.
can you explain what is the bypass switch? Number 7.
Oh, okay. Oh, bypass switch is this switch. Bypass switch means when current is not flowing through resistance, then current is flowing through the switch. That's why it is called the bypass switch.
Thank you.
Yeah, that's why it is called bypass switch. Bypass means when current is not flowing through resistance. Bypass means detour it. Yeah, that is only the meaning. Oh, Kamana, you opened the eCourseware, right?
Yes, Dr. Ali.
Yeah. No, I mean from there you are looking the questions, right? Yeah.
Yeah, I'm using computer and also
Yeah.
laptop. That's why.
Yeah. I know. Okay, that's fine. So everybody, as I said, that already these questions are uploaded on the eCourseware. You will find the class 18. Okay, so therefore everybody, you keep going, you keep trying, take your time, and then once you are done, upload on the Dropbox. Class quiz 2, the name of the Dropbox. So right now I am going to extend the time until noon tomorrow. Okay. So does anybody have any questions, comment?
No, Dr. Ali, thank you.
Okay, so please you all keep going. So with that, I stop sharing here.